All right, so I guess we can get started. Sorry for the delay. Thanks everybody for coming out today. I'm really excited and honored to introduce our last colloquium speaker of the year, Vashti Sawtelle, and who I believe is our very first graduate student selected colloquium speaker, and we're really excited to have her here. So we first invited Vashti a long time ago before the pandemic, so we really appreciate her patience all this time. And back then, Andre Adler was really excited to be having a colloquium speaker who was in physics education research, and we're really deeply feeling his absence today. But we're glad to know that his legacy will live on, in part through colloquia like these, including one next fall in physics education research. So Vashti earned her PhD at Florida International University in 2011, specializing in physics education research, and she was a postdoctoral fellow at the University of Maryland before joining the faculty at Michigan State University in 2014, where she's currently an associate professor of physics and serves as the co-director of the Physics Education Research Lab. Her research focuses on how learning environments can support or hinder students from diverse backgrounds and how those students develop self-efficacy and science identities. And I know she'll be talking about that shortly. She's particularly interested in supporting students for transitioning from 2 to 4 year colleges, but today she'll be telling us about how interdisciplinary lab design can help support the development of self-efficacy for all students. And I think that this is something particularly relevant for our department now as we start to look back at our own curricula and think about how they impact equity and inclusion in our own department. So with that, I'd like to have you all join me in welcoming Vashti. Thank you.
Thank you, Marco. And thank you also for your patience in getting me to here over a year ago of invitation and multiple attempts to schedule and reschedule. So I appreciate your patience as well. I am also just super thrilled to be invited by the students. I think that's a really great idea. So I want to applaud the department for allowing that to be possible, because I think that's just an amazing way to engage student interest in these big departmental events. Just let me flag as I get started here, make sure everybody's seeing a screen that has a title and looks like a PowerPoint slide. Yeah, cool. And then the other thing I just want to flag is my work is qualitative, and so I'm going to be sharing some video clips throughout. If your internet is on the slower side, feel free to turn off your video whenever I share a video clip, and that just might help things, transfer across easier for you as I share those. Okay, so let me get started by saying, first of all, I am jointly appointed at Michigan State between the Lyman Briggs College and the Department of Physics and Astronomy. What that really means is Lyman Briggs College is a small residential college on campus that caters to students who want degrees that both explore science and the history, philosophy, and sociology of science. So I have colleagues down the hall who are historians of gender and science, who study transsexual identities in science. Just really great environment, and they are constantly pushing my thinking as we embark teaching together in our science classes. Today, I'm going to be talking about an old shtick of mine, which is thinking just about how inclusion and diversity can inform our teaching and how we can build those practices into our classroom designs. But as Marco said, my research areas include both 2-year, 4-year college transitions, and in particular, the theory around how to support this affective dimension of students' development. Okay, so what I'm going to start with, and especially I felt this was necessary since I was invited by the students, is to just talk about who I am and how I got to where I am, because I think that acknowledging tricky paths is an important thing, that we don't all just follow linear paths to where we are. I want to talk about my research, which I'm going to ground in building a relationship with physics. I'm going to spend most of my time talking about a particular teaching environment that we designed that comes out of the research. And then I'll circle back to research at the end to think about how to assess this kind of design. And throughout this whole thing, I hope you see a thread of creating inclusive communities and all of my work. That's part of what I do and who I am. Before I get started, I want to ask you to tell me who I'm talking to. So let's just use the reaction button. Just raise your hand. If you are an undergraduate student, is that here? Is there anybody here that looks like that? No, okay, okay. How about if you're a graduate student? Okay, okay, good, thank you, thank you. Go ahead and put your hand down. And if you identify just as a researcher, and so you're not necessarily faculty, you just do research. Okay, thank you. If you're a faculty member? Cool. Nice, thank you. Oh, sorry, I'm scrolling and scrolled my thing. And then is there anyone from administration? Every now and then I have someone who is like a dean or something like that in the audience. Okay, okay. Thank you. I appreciate your participation. It helps me orient to who I'm speaking to. So I see mostly graduate students and mostly faculty in this audience. So that's helpful for me to know. Well, let me tell you something about me. First of all, as I'm a gardener, I love to grow things. Right now is my season in Michigan, where everything is becoming alive, and it just gives me great pleasure. I'm also a mother of 2 small children. It is almost 5 here, so I apologize in advance if my 5-year-old decides that that's supposed to be in the end of my day and comes in, even though he knows I'm in a very important meeting, as he says. I'm a physicist. That's a big part of my identity, and it's a big part of my identity on my campus. I chose this image because my world before I became a physics education researcher was mostly a condensed matter world, and so that's the area of physics I most identify with. I am a first-generation college student from the middle of nowhere, Ohio, from a very low-income family, and that is also a big part of my identity and affects how I do my work. And then I am a white cisgender heterosexual woman, and that impacts some of these things that I talk about. I just said I'm from the middle of nowhere, Ohio. I'm a first generation college student. Nobody I knew except for my teachers had a bachelor's degree even. And so I had no idea what it meant to go to college. So when I was choosing college, I chose based on those recruitment flyers that they send you. And I wanted some place that had snow. It's very great criteria. And that took me to Grinnell College in Iowa, which was actually a great experience. It's a liberal arts college in the middle of cornfields in Iowa. Really small class sizes. I'm grateful for that experience because I think I might have gotten lost in a place like where I work today with lecture halls of 300 plus people. And I want to tell a little bit about my path. So I was a physics major at Grinnell College. And my physics major decision, I feel, is an interesting one because I actually decided to be a physics major because I couldn't figure out modern physics. I was taking a modern physics class and I was bombing it. And I was like, this is a weird experience for me to be in a class. I just can't wrap my head around this. What is going on here? And maybe it says something about who I am as a person that I chose the thing that was giving me the most trouble to continue on to study, but that is honest to God what I did. As I said, I want to understand this thing that is so hard for me to understand. At the same time, I was taking linear algebra, and it was the place where math was always one of my favorites. And linear algebra was a place where I started to see complicated system level kind of mathematics actually telling me things, as opposed to just like slope kind of problems telling me things. And the other part of my undergraduate experience is I had the opportunity to go spend a semester at Oak Ridge National Lab in Tennessee. This was a really important experience. It actually got me my job post undergraduate bachelor's degree. But the other thing that happened here is I had a lot of experiences with scientists, staff scientists in the lab that made me feel like I didn't really belong. Comments about women don't belong in the lab, Are you sure your partner is okay with you pursuing this degree? Things that you think about as like storybooks. And I was like, I didn't know this actually happened. And so that was a really formative time for me to again, maybe push back on a system. Same idea, I couldn't understand modern physics, so I chose it. Someone was telling me I didn't belong here, so by golly, I do. You know, maybe that's just who I am, as challenging things. And from that experience, I went straight from my bachelor's degree and I got a job. And I worked at a place called Battelle Memorial Institute. It's a non-for-profit, does a lot of government contract work. They always describe themselves as big R, little d, and the research and development piece. So they do some development and the research is towards scale, but it's a research lab. And I worked in the clean room. I did a lot of wet bench physics, a lot of chemical vapor deposition, a lot of designing of resistance materials and things like that. And I would do a lot of quality assurance checks on designs. And it was a good job. It was a good company, a good job, had interesting science. I got opportunities to engage with. I really enjoyed it. At the same time, I was tutoring at a local high school. And I had this experience where 14-year-olds that I was tutoring were already being told that they weren't good enough to be a science major, that they wouldn't succeed in upper level math classes. And I was like, how do you figure this out at 14? Like, there's still so much life to live. How do you know anything about what you're going to do at 14? So I found myself asking these questions about who gets to do physics, who gets directed out of physics before they even have a chance, maybe before they even take a first physics class in high school. And what happens if you don't have a support group to get you through the bumpy spots, right? So if you don't have the people who tell you, of course you can do this. And that is what pushed me to go back to graduate school, actually, and I'm just gonna put all those up. That's what pushed me to go back to graduate school, and specifically to answer these questions about who gets to and what kind of barriers and support them in that. And that's actually why I chose Florida International University in Miami. It is 67% first generation, 86% immigrant population, Hispanic serving institution, all sorts of really good spaces to ask questions about who gets to. And from there, I went to University of Maryland, where I got to expand that kind of thinking to ask for physics for life science students who are often thought of not physics people. How do we create classes that actually support them in learning physics? And I'm going to speak more on that topic today. Let me see what's next here. And so that all leads me to where I am today. I am at Michigan State University. I co-direct the Physics Education Research Lab. This is the current Spring 21 a list of people who are in our lab. So we're a big group, a lot of people. We have a lot of mentor faculty, grad students, postdocs, and we actually employ a lot of undergraduate researchers. It's just part of who we are and what we do. I often say at this point to a department that it doesn't have a PER program, if anybody out there is like, I want to know a little bit more about PER, I invite you to write down my email and send me questions. I'm happy to connect you with groups if you want to learn more about physics education research. I also want to acknowledge before I go any further that the people who really influence my thinking, these are other physics education researchers who really influence my thinking, and the things I will talk about today are part of thinking with these folks. Okay, so now I'm going to get to the meat of it. Let me check time. Good. So the big thing that starts my work and my interest is I look for phenomenon. Right? So one of the phenomenon you all have probably seen are charts like this, where this is showing you on the left-hand side of this plot is all STEM majors. On the right-hand side of this plot are physics majors. And while you might see that both of these lines are sloped upward, the slopes are different, and so the gap is widening. More and more people are choosing STEM, but fewer and fewer people are choosing physics. And I was just saying to the students, some of the talks I give are actually to departments who are in danger of losing their physics programs. because so few students are choosing physics majors, that the universities are actually starting to talk about closing or condensing physics programs into physical science programs. And if we look at that problem a little more fine-grained and look closer at it, this is showing you the percent of undergraduate degrees that are awarded to women specifically, and I should define here, STEM is science, technology, engineering, and math fields. And it's broken down by different fields. And so down here at the bottom is physics, and it's clustered with engineering and computer science. And what I want you to pay attention to here, so this is holding steady over the last 15-ish years at about 21% of bachelor's degrees in physics are awarded to women. What I want you to notice here is that that's very different than mathematics, right, which is above here at 40%, and it's very different than chemistry, which is up here nearing 50%. And so one of the things that I always think about here is like chemistry and math both require the same kind of mathematical thinking. They take the same courses even as a lot of our physics majors do. But why then do we see women choosing those degrees and not our physics degrees? And that's a phenomenon, right? That's a thing that I can investigate and start taking apart and try and figure out the underlying mechanism behind it. I'll add one more layer to this, and that is if you take the intersection of women and race, and you look at our production of physics degrees from that angle, and I'm going to just focus on the bachelor's degrees. And so this is showing you it's women, but broken down by race. So this is a stacked bar where you're showing at the bottom, it's white women, and then Asian women, Hispanic women, African-American women. And what I want you to just notice here are these are numbers, right? So in 2008, we had 12 Black women who earned bachelor's degrees in physics. And 2012, there were 16, not 16%, but 16. And so if we think about the phenomenon here, the phenomenon is that some people, many people, are encountering our courses, right? They take them as part of prereqs for their programs. They might encounter our content and our understanding of the world, but they do not choose our degree programs. And so I'm curious about why that is. And I'm curious about if there are barriers or structural things that we're putting up in our physics programs that keep people out or push people away. So with that, let me show my first video. So if your internet is slow, you might turn your camera off. We're gonna flip around. Oh man, here. Okay. So I should say this clip comes from a well-known show called Big Bang Theory. It's from one of their early seasons, to give credit to the Big Bang Theory and the way they changed their shows. But it shows a lot of what I want to show here.
Damn it! Look, there's no need to get frustrated. People learn at different rates. Unlike objects falling in a vacuum, which... MA equals MG...
Squared?
No.
Aristotle?
No.
5?
Oh.
Then I don't know.
Why are you crying?
Because I'm stupid!
Well, that's no reason to cry. One cries because one is sad. For example, I cry because others are stupid and it makes me sad.
Okay. So what I want to highlight about this clip is that even if you didn't know the show Big Bang Theory, you would immediately know who the physicist is supposed to be in this clip, right? And let me see if I can't see my little cursor, right? It's supposed to be this white man standing in front of a whiteboard with a marker, a bunch of equations written on the board, and he's quizzing the woman on the couch, right? That is our cultural understanding of what it means to be a physics person. The other thing I want to draw your attention to is, well, maybe can I? There, yeah, is the reaction of Penny in this clip also, where she ends up putting her head in her hands and crying and saying, "I'm stupid." And this is also cultural understanding, right, of what it means to be someone who's trying to learn physics, is that it makes you feel dumb, it makes you feel like crying, it makes you feel like crumpling up. And regardless of whether you like the show, my parents love this show. It is their basis of understanding of what physics is. So, I have to interact with it. Regardless of whether you like the show, it is long-standing and has a lot of popularity. So it is part of our culture. And what I think it really does is tells us something about how the United States understands who physicists are and who scientists are, even in the more updated versions of this. And when we look at students, we see elements of this same kind of picture showing up in the way they talk about physics. So this is a quote from a student that was in some of our data, where she says, "I don't need physics. It's not really a key aspect in my future, or I don't believe it will be. It's more of a requirement. I just have to get through it." And what I want to start with in my work is saying that these assumptions, these cultural norms, are part of our classrooms, whether we want them to be or not. And so what we have to do is we have to engage with them in designing our classrooms and think about how they have implications for how our students are learning. I see a hand raised. Is this typical in the colloquium to pause and ask and take questions in the middle? Just asking for norms here.
It is typical, but I don't think Clayton has his hand up for the question.
Oh, okay. It just happened to show up in my screen. Thank you for the clarification. Okay, so yeah, so where was I? So one of the central things about my work is I am trying to create spaces where physics is considered to be inclusive. And I want to just pause here and define what I mean by inclusive. And here I'm going to lean on a couple of other scholars. So inclusion is different than diversity. It's an environment where members feel welcome, supported, and valued. And if we add on to that, I think it's really important that we understand that inclusion means that we understand that people cannot be separated from their larger personal identities. And what this quote says, right, is that what's important is that faculty mentor has the ability and desire to show empathy with those personal identities. So we don't have to share the personal identities, but we have to be able to develop empathy with those. And so when I think of inclusion, what I am thinking of are people from a large walk of backgrounds who come in and feel welcome, supported, and valued. And in particular, I think about designing classrooms where that is the case. So let me tell you about my research that then informs my classroom designs. So the central construct that I work with is what I call a relationship with the discipline. And in particular, I'm thinking about the relationship as influencing disciplinary practice. And the relationship here has interacting constructs. That's what I'm trying to show with these double-headed arrows. Affect means like your emotions or how you feel, the softer side of things. Identity is how we see ourselves, like who are we and how do we want to be perceived? And the beliefs are often, in my work, are often, what do you think physics is? What does it count as? And what counts as maybe other things like biology or other spaces? And in work, so this, what do I do for physics education research? A good science needs a good laboratory and detectors. And so the thing that I do in my work is I have two kinds of laboratories I work in. One is these introductory physics for life science majors courses. And then the other laboratory I work in is in this transfer space from community colleges to four-year colleges. What are my detectors? How do I actually see what I'm trying to see? I use qualitative methods largely. And one of the anchors for qualitative work to say that it belongs and that it's true evidence is that you do multiple kinds of data collection and you put them all together to make sure they tell the same story. That's called triangulation. And so I use a lot of observations. So I record video of students working in their classes. I'll put that camera up for the entire semester and record every lecture or every class period. We do some pre-post surveys, but not a ton. I use journal entries and interviews are the bread and butter of my work. So this is asking students to reflect on or to connect with a particular experience and tell me more about it. And so let me just give you a very quick example of how that looks in my work. And I'm going to take the construct of mindset to do that. And so mindset and my relationship exists here between the what do we think physics is and how do we feel about it. And what we've done in our work, so let me just define this. So mindset are your beliefs about the nature of intelligence. And in particular, it's how those beliefs influence how you respond to a challenging situation. So if you have a failure, what do you think that failure means? Does it mean you're stupid and you can't do this? Or does it mean it's a learning opportunity and you can grow? Sometimes this also gets the label of learning orientations, if you've ever heard of that, like a performance orientation or a learning orientation. In our work, and this is just an example of our work, we were trying to understand how students respond to these challenges. So we're not necessarily focused on that, do they think they have a fixed mindset or a growth mindset? We're more interested in asking when students encounter this challenge, how do they respond? And how is that different for different disciplines? And so I want to give you the example of talking with a student that we'll call Casey. And Casey, we're asking questions about Casey's experience with physics. She was an introductory physics student who was a biology major at the time. And we're just asking her about her set of experiences with physics. And she tells us about this experience in high school. So she says, when I was in high school, I went to the physics summer camp and we got to tour everything. And then we worked with a bunch of simulations and had lectures from faculty and staff. And this was the summer after my sophomore year of high school, so 4 years ago, I guess. And it was just way over my head. I had no background and I really didn't know what was happening. And so in our work, what we'll do is we'll look and see what was the challenging situation that Casey is talking about. And so I call this coding. I don't mean writing code. I mean tagging. So I code this to say, okay, the challenging situation was this summer camp where she was working with simulations and she had lectures. And then I ask, how did she respond to this challenging situation? The way over my head is the evidence of challenge. And what Casey says is, I found this was interesting, but I could never do this. I used to want to do astrophysics. And then after I did that, I was like, nope, this is not for me. And so what we would say from this is that this is a fixed mindset, right? Or this is approaching a negative response to a challenge where she gives up. She says, this is not for me. She doesn't say, oh, how this is really fascinating and challenging. Like, I want to do more of this. I want to solve more of these problems or puzzles. And from this work, we have lots of these kinds of data. We put them all together and we find things that really matter how students take up these challenging situations. So some of our work says that when you're looking at that challenge, what really matters is who's around you. So how are your peers taking up that challenge? Are they seeing it as something to learn from and grow from, or are they seeing it as evidence of that they need to give up? How does your instructor orient to that? So is getting a below average grade on an exam, is it just an indicator that maybe you should try something else? Or is it an opportunity for you to learn and grow how to take exams? Grading structures and norms, and then also just your interest in the actual subject. We find that can sort of balance out some of these other things. But the other thing that we find in these data that is influential on how students respond to these challenges are things like, what else do they have to be responsible for outside of class? Are they part of a marginalized culture in US? What does the US culture tell us about what they're supposed to be able to do or who they're supposed to be in order to do this? A lot of family stories about who is the math one and who is the art one, maybe in their families, or have they had experience with successes in their K-12 schooling? So we're at the university level, right? So in the K-12 schooling, did they have those successes or failures? And these last ones are the ones that maybe are surprising to some of us, that they actually influence the way that students respond to challenges in the moment. We often think of it as just the actual classroom, as opposed to all of those outside influences that really respond. But if I connect this to other folks' work, I'm less surprised. This shows up in larger studies. So this is just a quick snapshot from a paper by Leslie et al. And published in Science in 2015. And what they did is they surveyed practicing scientists, so folks who are working in the field, not students. And they asked them a bunch of questions that you can collapse all together to basically say they're asking folks to understand, to be successful in this field, you have to be innately good at it, or can you learn to be good in this field? And what they did is they correlated that value, right? So if you thought that you needed to be innately good, you're farther up on the x-axis. They correlated that with the percent of US PhDs in that field who are female, and then there's another plot in the paper that is for people of color. And what they found was a negative correlation with these numbers. So in other words, physics is a field that people, practicing physicists, believe you have to be innately good at, you have to be naturally smart at to be successful. And we are also a field that has very few women. Compare that to neuroscience or molecular biology, where practicing scientists believe that you can learn to do this. And we see more women PhDs in those fields. And so this is the negative correlation. They did this with humanities, and they also did it with people of color, if you want to go look at this. But the point here is to say that I think what this is saying between my work and this kind of work is saying that those outside systems, those bigger beliefs about who can and who does do physics, permeate all parts of us. They permeate our students. They also permeate us and who we think is ready to do physics and who can learn to do physics. Okay, so with that, I'm going to transition slightly into using this information to design a classroom. And I am probably going to have to skip some slides based on time. So I can always answer some questions, but I want to make sure there's time for questions. So I won't give all of these slides. So one of the spaces that we might think about in asking how do we design classrooms is where do we have the most students? And so this is just a chart that one of my grad students made actually of Michigan State numbers of who are the students that are taking our intro physics classes. So it's showing you that the largest number of students who take our intro physics classes are life science majors, and the smallest number of students who take our intro physics classes are physics majors. And one thing that is important to us is that for many of the life science students, this intro physics sequence is likely the only physics class they will ever take. And I often think of this as my future doctor, right? And how do I want them to describe their physics experience when I say I'm a physicist? You probably have the experience of people going, whoa, you must be so smart. Or, oh man, I hated that class, please don't quiz me, or something like that. How could we change that perception as part of where I'm coming from? Let me just take a pause here and look, let me decide where to go next. I think I'm going to skip ahead to the design aspect for the sake of time. So this slide is not going to make sense because you didn't see the bit about Violet, but Violet is a student in our set of data that describes what she expects physics to be as painful, and that she thinks she actually says it's going to make my life a living hell. And then what we see is through a class which really asks her to bring her biology knowledge into the classroom, we see her start to change her relationship with physics in a way that actually changes how she engages with the physics content. And so what we are thinking about is designing classes for students who have these negative perceptions of physics. And in particular, I'm going to be focused on life science students because those are the dominant group of students that we teach. And so let me tell you a little bit about this class that we designed, which we call Briggs Life Science Studio, BLISS Physics. That acronym was chosen very intentionally because we want to keep the affective piece front and center in our design. And so when we designed this class, one thing that we focused on doing for thinking about these life science students and the things that they actually care about and do is we want to bring big disciplinary ideas into interaction. We don't want to focus on rockets and roller coasters, but rather we want to ask what kinds of content do students in life science classes see that physics can add to. So some examples here are free energy, diffusion. And for example, what does physics have to add here is you might say in biology, they do a lot of work with free energy. But the way that students understand entropy is this just big, broad disorder. Disorder increases. And so a thing that physics can add to this story is how does an understanding of microstates and probability actually change the way you understand how to calculate or understand what free energy is, for example. We ask students to actually reconcile those contradictory ideas. So instead of just leaving one idea at the door and engaging with the physics idea, we say, bring it in, tell us what doesn't match, and let's unpack it and figure out at the base level what's going on here. So one of my standard examples here is ATP hydrolysis and chemical energy. How is it that ATP is the energetic, brings energy into the interaction if it takes energy to break a bond? How does that work? We create a classroom norm of articulating and justifying assumptions. Biology majors don't live in a frictionless vacuum world, and so we don't ask them to. We ask, when is it appropriate to treat this as frictionless, and when do we actually need to think about air resistance, that kind of thing. To that end, then you also have to give credit for that kind of thinking. So you have to give credit for more than just the right answer. At the end of the day, you have to give credit for articulating those norms and maybe making a different choice than you would have. And then this is just a qualitative way of describing this, but discursive patterns means letting students know when they did well. And so one of the things here is when students bring an idea in from biology, instead of being like, I don't know biology, I don't want to deal with that, you have to actually engage with it and unpack it with these students. And so I'm again just skipping around here for time, so bear with me. And so we
did start a little late, so if you want to take a few extra minutes, don't worry about it.
Okay, I don't know what norms are, so I'm just trying to keep time. Thank you, Marco, for clarifying. I will take a few extra minutes then, because I think that will give us time for questions. In doing this work and designing this work, I often say I hate writing physics problems. It's not the thing I enjoy. So I like to borrow from people as much as I can. And so when we designed these curriculum, we borrowed from a lot of folks. And this is just a list of some of those folks across the country that have done work for physics for life sciences. If your department, I haven't heard this, but if your department is interested in thinking about their life science redesign, I just want to note that a lot of these folks have come together in a new kind of system, which is called the Living Physics Portal, to contribute materials to an online system where you can just log in and find stuff. And they're committed to open source so that you're not paying for packets or books, but really you can get what you need and adapt it. And they have everything from homework problems to like laboratory exercises and that sort of thing there. So we drew from a lot of these materials. I've contributed some materials to the Living Physics Portal now that we've written different materials. And then when our key designs, I skipped this slide, but we teach a studio class. So it's actually the lecture and the lab are combined together into one experience for students. What that allows us to do is to flip the cycle and encourage students to actually design experiments to uncover the basic physics instead of asking them to learn the physics and then check it out in lab. So our key components are we ask students to design experiments. We ask them to actually connect it to biology. I worked with a biophysicist to do a lot of this work to make sure my biology was right. We do a lot of coding. The reason why we do a lot of coding is because a lot of paper pencil physics is single particle. If you want to go to multi-particle systems like are present in biology, you need to be able to do iterations. And a lot of my students don't have the confidence in the math to do that. And so we use code to let them do it without banging their heads against the math. And then there's a strong emphasis on collaboration and building that group work and team element. If you're curious about the details, the way that we've structured this is we take our big idea as diffusion for the first semester mechanics. That means we do a lot of entropy instead of just a little bit of entropy, but we also think about momentum conservation and forces in the context of diffusion. And then the second semester, we take our central as dipoles, and the whole point is to get to light. So a full third of my second semester course is about light and oscillating dipoles. Our other big design principles in the content is that we focus on physics as identifying and articulating systems and system boundaries. And so this question of like, when can we say that something is frictionless is a real question that we want to ask every time we bring up a new situation. And then the second piece of this, which is, you know, in the heart of most physicists, is that it's also true, though, biologists, sometimes you have to simplify, and that's okay. And so to model biology, we sometimes need to make reasonable assumptions and simplifications, and that's worth doing. And so let me just give you a quick example of how we do this, I think. Yeah. So one of the things that we do is we use Visual Python for the code. We use the GlowScript interface because it's on the browser, so it doesn't require me to know anything about computer power of individual students. And what we do is we use what's called minimally working programs. So the programs will run, they will generate a picture, but they will have the physics wrong. And then what we ask students to do is to find the line in the code where the physics is, and then edit that. So they're really only trying to write that F equals ma kind of equation in the code language. Or what we really do in this semester is we start from two balls collide and they need to bounce off each other instead of passing through. And then we keep adapting that to now we have multi-particles. I think this will run. We have multiple particles interacting. We can change the sizes of these, and this is all momentum conservation. And then we add electric forces so they don't actually have to hit, so they can actually rebound within a certain distance and that sort of thing. And all of this that we do is toward modeling this phenomena of diffusion that the students are really familiar with. Right, and so the end of this little unit is they end up writing code that models larger molecules in a system of small molecules. They can put these tracers on it that they see things like random motion are a result of interactions with particles. And then we connect that, I think this is my next slide, we connect this with biology to say, okay, so when you look at simulations of proteins folding, what are they not showing you? What else is going on here that this protein is not just wiggling on its own? What else is happening in the background? And this is an example of how we bring these biology ideas directly into interaction with our physics ideas. Most of them have seen this kind of simulation before, so it is actually quite satisfying to get to the like, oh my gosh, there's no water here, and all we did in the code was make the water not visible in that line. Oh my gosh. Okay. And then the last part to this that we do in our design is we want to take this to the experimental level too. And so what we have done is leverage some other people's great designs and adapted them to our classrooms. We have my postdoc mentor always thought this was so cool that in our physics labs we had microscopes. To me, I'm not sure why that's so amazingly cool. But what you can't really see here is that these particles are wiggling. These are just silica beads suspended in a solution. But what we have students do is use video capture software to actually capture these silica beads oscillating. And then we have them track it and show that they get that same entropic diffusion random motion happening in real life, that these are not just computer simulations, but it really explains what's happening in real life. They design experiments here where they change the size of the silica bead, they change the solution, and they see what happens. How does that influence the coefficient in front of the diffusion coefficient? Right, and what we do is explicitly connect that computational activity to the real life activity. So ask them to compare and contrast what kind of simplifications is that computational code making that we can't make in real life, and vice versa. Am I still okay, Marco?
Yeah.
Okay. So then I'm going to ask the question of how do we assess this design? I'm actually going to skip this because we could ask all kinds of pre-post questions that I don't actually care about. What I actually care about is how do we assess then for the thing that I said at the beginning, for those perceptions and the attitudes? Have we changed anything about what our design was actually intended to design? And so this is where the research comes back in, right? That this is not just as simple as you do it and then you say, good job, pat yourself on the back, but you have to ask a harder question. So let me go back to my construct of a relationship with a discipline. And this time I'm going to focus on what I'm going to call relevance. And relevance here is going to be a linker between who do I think I am and how does that influence how I feel about physics? And then what do I think physics is? And how do I think about, and how does that influence how I feel about physics? And this was work all from my graduate student Abhilash Nair's dissertation. He's done and now works not in academia at all, but makes a lot of money at FICO. But this is based on his work. So what Abhilash posited was that relevance can be a powerful construct for understanding how students can shift from seeing physics as a hurdle to overcome to a meaningful experience in their life. And so we're going to use just one student again as an example. We're going to call him Miles. And Miles, in our original work, his only experience with physics was an MCAT study course. And what he saw, he was a tutor for chem at the time, and he saw these kids coming out of the MCAT study course from the physics side, and they just looked awful. And they said it was terrible, and that he was terrified about starting his physics courses because of this experience. And at the end, he talked about carrying his love for physics and his unique relationship with the Bliss Physics, that's our course, throughout all of my endeavors. And he's currently in medical school doing amazing things. And the work that Abhilash did here, I'm not going to unpack this figure, just let it stand, it's okay. But the work that Abhilash did was thinking about an individual as interacting with lots of systems of layers here to understand what relevance means. And so if you put the individual at the center, then you can think about their course and their major experience. You can think about their home life. You can think about society, and it keeps going bigger and bigger and bigger. And you can think about relevance as connecting any of those across any of those boundaries. This is just acknowledging these are all the cases that Abhilash did to pull this work, and I'm just focusing on Miles. I said all of this already, so I'm going to skip it. So initially, Miles thought of physics. He didn't actually have a good idea about what counted as physics, but he knew it was required for his biochem major. And he knew that some other folks that he knew had negative experiences with it. That's really all he knew about physics. Whereas he had a very advanced understanding of chemistry and biochemistry, a very advanced understanding of those. Headings got mixed up here. And this is just showing you, this is the set of data that we have with Miles. This is the idea of triangulation. We have many pieces of data that we connect together to tell his story. But what I'm going to focus on is just Miles interacting with that same code that I showed you a few minutes ago. And so we're going to talk, you're going to see video from these three students. They were in a group together. Miles is the student way at the end by the wall, and he's going to talk the most. Amy is in the middle, and she's going to say some things here. And what they're doing is they're trying to work with this code.
It's fine.
And V1 final was what?
Negative 29.6.
Wait, is it in joules or meters per second?
We're doing the meters per second.
Why? The water.
Because
are these gonna cancel? Oh, these will cancel. Wow.
it's okay.
So serious.
Life will go on.
So it may have been a little hard to tell here, but what they're doing is they're trying to do that translation work. What's the analytic version of the physics, and they're trying to write the thing that they would put into the code. And Miles is struggling and he's feeling crappy about it is the take home of this clip. And so what happens next is they call over an undergraduate learning assistant to ask a question. It takes a long time. Miles says he's sorry, he's the weakest link in this group, and that he just apologizes for slowing everybody down all the time. Ooh, I think this is in the wrong place. And he says, I'm just plugging in numbers because I can't see it in my head and it's really bothering me. And then we come back to the next day and they actually write the code. Right? And I want you to pay attention to how he experiences the code. Oh, I already said this, sorry.
Number of small particles, number of large particles.
Okay, so like if it's smaller, it'll have more bounce back. If it's larger, it'll just like.
It'll have less of effect and less of a time frame.
Yeah. Right? Because there's like less of it to transfer, right? Can you think about it that way? Or?
I think so. It's like when the big one was like going fast, the little one it flowed way down to transfer like.
It transferred a lot.
They're all moving in like 3
Okay. That's fun.
That was cool. I like this. I feel bad for talking shit.
I like coding when it works.
I mean, I don't really like to code, but I like to see this stuff. That's cool.
Okay. Now on the code and observe. Okay, what do we do now? The best way to describe
The particles in the box. I don't know how I feel about.
Okay, so what I want to highlight from this bit is he was feeling like the weakest link. He was feeling not smart. He enters the code. He's never gonna be a coder, right? Like he's like, I don't really like to code, but I like to see this stuff. And so one thing the code is doing here is it's providing him a way of visualizing, which is what he was trying to do with the numbers in the first place. And so what he ends up liking about this is that he can actually see what he thought would happen. And so what happens for Miles as he continues with this course is that he gets a more well-developed picture about what counts as physics, and that physics is connected to things like chemistry and biology and biochem that he actually cares about and understands and enjoys. The other thing that I'm not showing you here, but for Miles, is that it ends up connecting to everyday phenomena that he is just interested in, like why do sunsets look the way they do and why does salt melt ice, which I know from chemistry, but physics can actually help me understand. And I think I'm going to skip this because of time.
Shaky.
And so what we learn from designing a course like this, one is that we can have some success. I'm showing you qualitative data from a set of students, right? But we can see this over and over again, that we can have some success of connecting to the other things that students care about in designing this class. And when we do that, what we learn is that students can and will build complex and robust models of physics, and that they will see the relevance of physics. And what that ultimately does is shifts their relationship with physics to the point where Miles is actually talking really positively about physics by the time he leaves. And I think, yeah, and with that, I will end and I'll say thank you. And I always, at this stage in the pandemic, I just acknowledge that this is my working environment with this kind of thing happening in the background, and hopefully it makes some of you smile to see this 2-year-old bouncing around. Thank you.
All right, thank you very much, Vashti. That was great. So we can take some questions now, and I see Paul already has his hand raised, so why don't you take it away, Paul? Sorry, you're muted, Paul.
Dang, all right, thanks for the great talk. Sorry about that. So as part of the Bliss model, you said one of the first things was that they get to design their own experiments, in which I'm kind of interested in this, like being able to do some self-determined learning. And it seems like that's a good way to build this identity and like self-efficacy and all these different things that seem really good, but it's also like we have to get through the material. How do we not let this self-design go off the rails, and how do we ensure they actually get somewhere? So can you speak to how you try to facilitate that?
Yeah, I think one of the hardest things to convey when people talk about physics by inquiry or where they talk about students designing, one of the hardest things to convey is what the teacher's role and that environment is. And so let me just describe for you the prep meeting that would be a precursor to one of those sessions where I have across 4 sections, I'll have 2 graduate students and 7 undergraduate learning assistants who are spread across all different versions of these classes. But in the end, we have about 3 instructors in the room at any given time. And in that prep meeting, what we're doing is we're going through the material, but we're also generating every idea we possibly can that will work in these designs. So as teachers, we have thought through what kinds of designs will students possibly come up with? How do we push them back onto a path that will work? And if students are just like not even sure what to do, what are the simplest and easiest paths forward, right? And that work is a lot of work. And then the real expert in the room, which I would say a real expert in the room can also respond to those random ideas that you never thought of, which are sometimes really good. And that person has to know their physics inside and out and be able to see down the road to how that experimental design will work. If you're a new person and you're trying this out, you just don't give them that freedom. You don't say you can design anything. And one of the pedagogical moves there is you tell students they have to come up with 3 designs and then they have to get approved for one to move forward. And so pedagogically, what you do is you come around and you look for the designs that you know will work. In 3, they're going to generate one of those and you send them down that path rather than the other path. And that still takes time. It still takes time away from it's much faster to just tell people what they need to know. But if you're okay with that idea just on the outset, then there are ways to make that shorter in the end.
Thank you.
See David has his hand raised.
Hi, thanks very much for a wonderful talk. Physics in particular has a huge problem with reaching people because of a long history of trying to repel people deliberately, very successfully. And reversing that is hard. Now, you've shown us that you can measure the impact of programs on students' retention of information, their development of skills, and even their immediate change of impression of the field. How about sort of longer term, changing of people's career paths? Do you measure students' eventual preferences to go into STEM fields? So for example, your student going into making a lot of money, as you said, applying their technical knowledge financially, that would be going into a STEM field by my metrics. So do you track that, and how do you track that? Because that's a very long-term measurement problem.
It is a really long-term problem. And so my short answer is no, I don't typically. That is my answer. Do people? Yes. But what I actually rely on quite a lot is the American Institute of Physics, the Statistical Resource Center does track this information. And if your institution gives them the information they need every year, they will track your students till PhD plus 10. That's what they do. So what I do is I rely on them to tell me about physics people and what kinds of changes might be influencing physics paths. Now, broader than that, I don't have those answers. And because most of my work is actually in the non-physics major tracks, I have not answered that kind of question longer term.
So what you just said was like a bombshell for me. I didn't know that the AIP did that. I don't know if the people around me do. If they don't, it sounds like we ought to.
Yeah. So I serve on their advisory board, and one of the things that I learned, I don't even know, I've been on that for a long time, is how very hard they work to keep all of their databases up to date so they can follow these students. And what they really need is your chair of your department, or if you have an undergraduate chair, like a chair of undergraduate, you just have to answer their emails. That's what they ask.
All right, I think we have a question from Shura.
Yeah, thank you. It was very interesting. Your experience is very instructive. I have a question to you about this boy who you showed felt better about physics as he went through your instruction. Do you have any data about his future success in the medical field? Presumably he wanted to go.
Is it just me that can't
I
hear?
I think you cut out, Shura. We can't hear you.
Oh no.
Can you hear us? Okay, well, maybe while this is figured out, we can, there's another question someone has. Should I take it? I guess I have one. So I'm interested in knowing what you think about implementing this kind of design in, existing kind of laboratory course structures where maybe universities, haven't allocated a budget for 3 people in a room at a time. Do you think that is feasible? Can this be accomplished in that kind of setting?
Yeah, I should have said right up front that the work that I was doing as a postdoc with Nexus Physics was exactly that. So it was a standard lecture lab separation where the only resources we had available was for a postdoc to do some of the work on developing these courses, and we had a couple graduate students who were doing their dissertation work on it as well. And so what we did was we did our best, is how I would say it, to make changes and accommodations in that existing structure. And the student I didn't show you, Violet, came out of that work. And what I would say is absolutely you can make impact there. It does change students' experiences, and we have lots of evidence of that. It changes both their the relationship part, but it also changes their disciplinary practice. We have lots of examples of changing how they think about problems and those kinds of courses. However, I think it is limited. Like if you can only work within your existing structures, then you can't do the work that like Paul was asking at the beginning of focusing on design, because your lecture in your lab might just be really disconnected. So the idea of designing something before you learn it is just not possible. And my what I would point folks to in that case is there is other work, University of Utah, George Washington University. There are places that have done that work in their lab setting alone. And what they really do is they just bust apart the existing lab structure and allow students to take 2 or 3 weeks on one lab experimental problem. So they really focus on developing those experimental skills, and they stop focusing on saying you need to reify content in that experimental setting. And in that way, you can still have some of those really rich experiences for students, but you have to be willing to let go of some structures. That's just it's always going to be true. You have to be willing to let go if you really want to change.
Thank you. Yeah, that's really instructive. I think we lost Shura, so I guess that question's just into the wind. Are there other questions from the audience? I can ask one more. So this was given in the context of a lab for non-majors. How far kind of into the physics major realm do you think this can be pushed? Can it be used in physics 1 labs for physics majors? Can it be used in advanced experimental labs? What are your thoughts on that?
Yeah, actually, I think that, so I often teach the intro class. I often teach non-intro classes as well in the physics department. And I think we can use some of these same principles in those other spaces, but you have to just change the what are you trying to connect with, right? It's no longer biology problems. And so one of the things is like just letting students let you know what is their interest. And so one thing I might do, or I do, is I create that project structure alongside my lecture class. So I ask students to do a deep dive in some physics area that they find cool and interesting, and let them, like, guide them through the research process of doing that, and ask that it connects to the physics content in some way. But physics is usually really easy to connect in some way. So I just ask them to do that work. And I think that it works. It works really well. The experimental side, I would actually argue that physics is much better about giving their majors that experience than they are about giving their non-majors that experience. So ad lab typically runs much more like a real research lab, where you have a big question and you spend multiple weeks trying to answer it, where people expect you to spend 7-10 hours a week in the lab and figuring this out. At my institution, we have a parallel course for entering physics majors, that it's like, if you declare yourself a major on the first semester, you get into one of these experimental labs, which is super cool. Electronics labs typically run like this. So I think we actually do it quite a lot in our physics majors. And one of the arguments I'm often saying is, like, can we think about that for more than physics majors? And it takes, the resources are different, right? Because usually our physics majors are, maybe we have a 10-person class, and now we have to be able to meet the needs of a 100-person class. And so you have to think about that a little bit differently. But yeah, that was the answer to your question.
Thank you. So I don't know if anyone else has questions. Okay, but otherwise, I guess we can just thank Vashti again. I really enjoyed this talk, and probably will be reaching out to you with more questions soon. So thank you very much for joining us all today.
Thank you. And thank you all for having me. I really appreciate it.
Thank you.
Thank you.
All right, bye.
Thank you.
Thank you.